right? Now, if you don't disturb the container, the liquid will be stable. The free surface of the liquid, the upper surface that is there, will be horizontal. Okay. Can any of you give an explanation? Why should the liquid surface be horizontal? Why can't it be in any other shape? Like almost horizontal, right? Why does the liquid always settle like that?
Sir, because the pressure is same everywhere.
See, if once it settles like that, the pressure will be same everywhere, no? Or which pressure are you talking about? Pressure on the upper surface or pressure on the lower surface?
On the upper surface.
On the upper surface, the pressure is same everywhere. So still, who is telling it to be flat? Why should, like, if the pressure is same, why should the surface be flat? I mean, suppose the surface is like this. Now also the pressure is same everywhere. Okay, P naught. Why can't it be like that? Why should it become flat? Okay. Actually, what happens? Suppose the surface is like this. Okay, not flat. Now you know pressure varies with depth. Okay. Let's assume the liquid settles like this. Is see the consider one point here A and consider one point here B. Both are exposed to atmosphere. So A should be at atmospheric pressure. B should also be at atmospheric pressure. Now if A is at atmospheric pressure, then you as well as B. If A is at atmospheric pressure, C cannot be at atmospheric pressure because it is deeper than A. It is inside the liquid. So pressure at C will be greater than atmospheric pressure. Now if pressure at C is more than atmospheric pressure, but the pressure at B is equal to atmospheric pressure itself, then what will happen? You consider the liquid imaginary cylindrical element like this. Pressure at C is more than P naught, but pressure at B is equal to P naught. Then what will happen? The force from the left side on the cylindrical element will be stronger because pressure is more. No, if pressure is more, the pressure that side is P naught only. Okay, but this side the pressure is more than P naught. So there'll be more force from the left side than from the right side. So what will happen? This liquid will move to the right side. And where will it go? Once the liquid moves to the right side, on the right side, the level will have to rise. So A level will come down, B level will go up. Okay, so finally the liquid will settle, the free surface of the liquid will settle horizontally. The main reason for this is that the pressure increases as you go in the downward direction. Okay, that is why the liquid settles horizontally. The pressure gradient is in the vertical direction. Gradient means what? Any quantity which varies from point to point. Okay. If a quantity varies from point to point, its variation is what you call as a gradient. Some of you may have heard about color gradients. Okay. Color gradually changes from one to another. You call that as color gradient. Similarly, you can talk about pressure gradient. As you move down, the pressure increases. Okay. So because the pressure gradient is in the downward direction, vertical direction, the free surface settles horizontally. Okay. That's the logic behind all this. Fine. Now consider this container itself. On the horizontal surface only. Let's say this is a tumbler with some water filled in it. Initially, when you don't disturb the tumbler, the water level will be horizontal. It will settle like this. But imagine pushing the tumbler to the right. If you suddenly push it to the right, or if you start moving it to the right, something which is initially at rest is being made to move. Means you are changing its velocity, means you are accelerating it. Okay. And for acceleration, you need to apply a force. So let's say by applying a force, you accelerate the tumbler. From your everyday experience, any one of you tell me what happens to the free surface of the liquid? Does it continue to remain horizontal or does it tilt? If it tilts, which way does it tilt? Okay, we imagine carefully and answer. I'll adjust the diagram by then. So if you exert a force and accelerate the tumbler, okay, let me show the force on this side itself just to avoid confusion. Will the free surface of the liquid still remain horizontal or will it tilt? We are accelerating it horizontally.
So the free surface will tilt.
The free surface will tilt. Okay. which way will it tilt? I mean, which side will go up, which side will go down?
The left side will go up, sir.
Correct, correct. Okay. If there's a cup filled with a liquid up to the top or maybe almost to the top and you pull it to the right side, you will see that the liquid spills out from the left side. So basically, when you accelerate this container to the right, what you will observe is something like this. Okay. On one side, the liquid level will go down, the other side, it will rise. Uh, for you to observe this for a significant amount of time, you need to keep on accelerating the container. Usually in daily life, what happens if you just push a water bottle, no, by some distance, you are accelerating it and again retarding it. Then you will see that the free surface will sway back and forth like this. But if you keep accelerating it in one direction, it will only get tilted in the other opposite direction. It will only rise up in the opposite direction. Okay. So if you maintain a constant acceleration, which is hard to do with the hand actually. You can't maintain constant acceleration with your hand. Okay. But if you can somehow maintain constant acceleration, you will see that the free surface of the liquid will no longer be horizontal, it will get tilted. Fine. And you can explain this on the basis of what we just discussed. Where the level of liquid is higher, or okay, if the surface is not horizontal, then at a certain depth, pressure at one point, in this case C, will be greater than pressure at another point, in this case B. And if pressure at C is greater than pressure at B, net force will be to the right and the liquid will accelerate to the right. And here the container is also accelerating, so the liquid has to accelerate. That is why you will see a tilted surface. Okay, let us derive expressions for pressure variation in a horizontally accelerated container. Suppose the container is accelerated to the right as shown in this diagram. Let's consider two random points inside the liquid. Let's call this as A and some other point here, let's call it as B. Now clearly A and B are not at the same depth, so their pressures will be different. Okay, and they have to be different. Why? Because the container is accelerating, liquid has to accelerate along with it. For the liquid to accelerate, pressure cannot be same on both sides. There has to be a pressure variation horizontally also. Okay, we'll derive an expression for that pressure variation now. Consider a cylindrical element of this liquid between A and B. Okay, I'll just give you hints. You'll have to do this on your own. Consider a cylindrical part of the liquid. Cross section will be taken as dA. Density of the liquid is rho. And this length, the distance between A and B, let's call it as x. Okay, we used to call depth as y. This horizontal distance, let's call it as x. Now, what is it that we want? We want the pressure difference between A and B. So let the pressure at A be PA, pressure at B be PB. Now, due to pressure at B, the liquid will be experiencing that cylindrical. You should be able to write the expression for that force. Due to pressure at A, the liquid, the cylinder like this, you should be able to write an expression for it. Of course, there will be vertical forces also. The weight of that cylindrical element will be acting. Force due to pressure from above will be there. Force due to pressure, okay. Different points, different pressures, no? So here the pressure is more. Here, as you go to the right side, the pressure will be lesser. So the force profile will be when. But these vertical forces don't really matter now. We want the pressure difference between A and B. So you will have to write a force equation. Newton's second law you will have to write in the horizontal direction. So the vertical forces won't really matter. So I'm removing them from the diagram. Now, this is a static liquid. What does that mean? Relative to container, it has settled. Right? We are somehow accelerating the container in such a way that the liquid does not move around. It has tilted, the free surface has tilted, and it has settled. So it's not tilting anymore. Fine. So relative to container, it is at rest, at equilibrium. Container is accelerating. So with respect to ground, the liquid is also accelerating along with the container. But with respect to container, it's at rest. Okay. At rest with rest. I mean, while pulling it or pushing it with bare hands, cannot do it. But let us imagine a situation like this. So yeah, I want you to write Newton's second law on that cylindrical part of the liquid. Now, the choice of reference frame is yours. You can write it with respect to container, in which case you'll have to include a pseudo force, or you can write Newton's second law with respect to ground also. Okay. You can choose the reference frame, that is your choice. Write an equation and derive PB minus PA. Horizontal pressure difference based on the acceleration. The answer will be in terms of density, of course. It will be in terms of these. Okay. Try this, all of you. I'll give you all 2 minutes. Okay. As I said, we just have to write Newton's second law to involve forces, which will involve pressures. Okay. Now the force from the right side is PB multiplied with A. Okay. Pressure at B multiplied with cross-sectional area dA. And force from the left side to the right side is PB multiplied with dA. And force from the right side acting to the left will be PA multiplied with dA. dA is the area of cross-section. Okay. Now, with respect to ground, if you see, that part of the liquid will be accelerating along with the container. Okay. Therefore, you will be writing pressure at B multiplied with the area of cross-section minus pressure at A multiplied with the area of cross-section. That's the net force to the right is equal to mass. How do we write mass? Area multiplied with the length. Cross-sectional area multiplied with the length. Okay. So mass multiplied with acceleration. dA gets cancelled. So you get pressure difference as rho A x. That's all. So if the container is accelerated horizontally and the liquid is static, means the liquid is also accelerated horizontally with respect to ground, then there will be a horizontal pressure variation. There has to be. Otherwise, how will the liquid accelerate? Okay. Only when there is pressure difference, there will be a net force acting on the liquid and it will be able to accelerate. Okay. So pressure at B, okay, this delta P is actually pressure at B minus pressure at A, right? So, and this is the positive term. That means pressure at B will be greater than pressure at A. Okay. Now, we assumed a case where the container is accelerated to the right side. And if container is accelerated to the right side, we see that pressure increases as you go to the left. Okay. See, there will be vertical pressure variation as usual. Gravity is there, no? So weight of the liquid will be there. As you go down, weight will increase, pressure will increase. So vertical pressure variation is there. Horizontal pressure variation is also there this time. Okay. So effective pressure variation or effective pressure gradient will now be somewhat like this. Like roughly, if you see on this liquid with respect to container, okay, if you look at the external forces acting on it, gravity will be acting this way, pseudo force will be acting this way. Okay, on the liquid as a whole, there will be mg here, mg like this, and ma like this when the container is accelerated horizontally. Okay, in such cases, effective gravity will be resultant of these two, root of g square plus a square, because g and a are not in the same direction. Had g and a been in the same direction, it would have been g plus a. Had g and a been in the opposite direction, you could have written g minus a. Okay, mg and ma being in opposite direction, you could have written g minus a. Here mg is downwards, ma is to the left. Their resultant will be there, no? How do you find resultant of two vectors which are perpendicular to each other? Root of a square plus b square. Okay, so I'll have to shorten this ma vector a little bit just to make the diagram look correct. Right. The resultant of mg and ma will be in this direction. So effective gravity will now be in this direction. And if effective gravity, this is m into g effective. If effective gravity is in this direction, the pressure gradient will be in that direction. Okay, that's the direction in which pressure actually increases. And if pressure gradient is in that direction, the free surface automatically settles perpendicular to the pressure gradient. The free surface always settles perpendicular to the pressure gradient. Remember that. Okay, when container is accelerated upward or downward or not accelerated, pressure gradient is in the vertical direction. So free surface will be horizontal. But if you accelerate the container horizontally, there will be vertical pressure variation and horizontal pressure variation. Effective pressure variation will be at an angle like this. And the free surface settles perpendicular to that angle, perpendicular to that direction. Okay, that is the nature of liquids. They will have to settle like that. They have no other choice. Okay. Fine. You can even find out the angle at which the free surface will be tilted. There are two different ways of doing it. I'll explain both of them to you. Now we know that the free surface settles perpendicular to the direction of maximum pressure gradient. Now the direction of maximum pressure gradient, how did we determine that direction? By taking resultant of mg and ma. Okay. What we now want to find out is the angle at which this surface will be tilted. Let's say with the horizontal, the angle is theta. Fine. If that angle is theta, then imagine this perpendicular direction. This is 90 degrees. This will be 90 minus theta. Okay. If that angle is theta, then the opposite side, this side is ma, this side is mg. Therefore, tan theta becomes ma equal to tan inverse of a by g. This is actually an angle which is familiar to us. We came across this, I think, once or twice before. One case where we came across this is the angle at which the bob settles if a cabin is accelerated horizontally with an acceleration a, and you suspend a bob from its ceiling. The bob settles at an angle with the vertical, or theta is equal to tan inverse a by g. Simple idea with respect, will be acting this way. Okay. mg vertically, ma horizontally. Then this angle theta becomes tan inverse a by g. Right? We came across this once again also in case of pseudo force. If there's a wedge like this and a block is placed on it, fine. If you accelerate, means tan theta is equal to a by g again. The block will neither slide down nor slide up. It will stay at that same level. Both will be accelerating horizontally. Okay. So here also, if the container is accelerated with the horizontal acceleration a, which is constant, then the liquid settles at an angle theta with the horizontal, where theta is given by tan inverse a by g. How did we derive this? We got the direction of effective pressure gradient, and free surface should be perpendicular to that. Based on that, we derived. There is another way also to derive. See, it's not the results that you need to remember. The methods are what you need to remember. Okay. So one method is to think of pressure gradient and the direction, liquid surface settling perpendicular to that direction. Another way to look at it is like this. We want the angle made by the free surface, right? So let's visualize the horizontal line here. This angle theta is what we want to derive. Consider this point, call this point as A, call this point as B, and the point which is vertically below A at the same depth as B, let's call it as C, will both be equal to atmospheric pressure because A and B are exposed to the atmosphere. Whereas pressure at C, there are two different ways in which you can express it. You can express pressure at C in terms of this depth if you want. You can express pressure at C in terms of how to write horizontal pressure variation, in terms of the horizontal acceleration. So pressure at C can be written as pressure at A plus rho Gy. That is in terms of B plus rho Ax, horizontal pressure variation. Now pressure at A is same as pressure at B. If these two are equal, that means these two should be equal. Okay. That means X density rho gets cancelled. You get Y by X is equal to A by G. And Y by X in the triangle, if you see ABC triangle, Y is opposite side, X is the adjacent side to theta. So Y by X simply becomes tan theta. So that way also you can say A is equal to G tan theta, or theta is equal to tan inverse A by G. That's what we are interested in. Okay. So if the acceleration is constant, then first we derive the expression for horizontal pressure variation. This is very useful. Horizontal pressure variation will be rho Ax. That means pressure distance x in the horizontal direction. And you know, vertically it anyway varies linearly only. P naught plus rho Gy. Linear variation, linear variation. Vertical variation is linear, horizontal variation is linear. So the surface will be a linear surface. Okay, like when you look from the side, it looks like a straight line. Actually, it's a flat surface, two-dimensional surface. So suppose this is the free surface of the liquid, it tilts like this. Okay, it's still a flat surface, but it's tilted. When you look at it from the side, you just see the line. Right. Let's consider another situation now. I want you all to try this, try to solve this. Just a moment, I'll draw a diagram. Okay. Assume there is a narrow horizontal tube like this. Okay. What I mean when I say narrow is this height is negligible. Okay. The length of the tube is quite significant. Let's assume the liquid's density is rho. and length of the tube is given as L. Cross-sectional area won't be needed. You can assume it whatever you want. Now, what I want you all to calculate is this tube, it's closed at both ends, okay? If this tube is rotated about one of its ends with a constant angular velocity omega, okay? I want you to derive the pressure difference or the pressure variation. So I'll have to give you 2 points to ask the pressure variation between them. Let's consider this as 1 point. The left end itself is one of the points, A. Other point, shall we take the right end or? Okay, let me see if you can do this. Take the other point as B. Now first, one of you tell me, from which side, okay, as this tube is rotated, from which side is the liquid more likely to leak out? If leakage ever happens, from which side is it more likely to leak out? A or B? Or is it equally likely to leak out from both sides?
From B, sir.
From B. Okay. That indirectly means that the pressure is higher at B. The liquid has a greater tendency to escape from B, means the pressure is higher at B. That is what you are saying. Okay. And what you said is correct only. Pressure at B will be greater than pressure at A. Now I want you all to derive an expression for pressure at B minus pressure at A. Think carefully and solve. The approach is the same. The liquid is already in the form of a cylinder, no? So you don't have to separately consider a cylindrical element. Based on pressures, write the forces. Based on forces, you write Newton's second law equation. From there, you will get the pressure difference. Okay. Try this, all of you. I'll give you all 2 minutes. Now, from the left side, there will be a force acting on this liquid, which is pressure at A multiplied with the area of cross section. Pressure at A, I'll call it as P1 just to avoid confusion. Okay. So the force from the left side will be P1 multiplied with the cross sectional area. Cross sectional area, I'll call it as S. That is up to us. You can call it whatever we want. Next, from the right side, based on the pressure there, P2, the force will be P2 multiplied with S. Just a moment. Okay. Now, this cylinder or the liquid inside it is rotating. If it is rotating, it must be accelerated. Okay. Net force is equal to mass into acceleration will give us the pressure difference that we are looking for, PB minus PA. Now, you know how the liquid is rotating. The center or the axis of rotation is this. Fine. If anything is rotating about an axis, there must be a net force directed towards the axis, centripetal force. Therefore, the equation you're going to write is net force towards the axis. That is P2S minus P1S. That's the net force towards the axis is equal to centripetal force. What is the formula for centripetal force? We know. Okay. But here is the tricky part. Effectively, what we are doing here is F net is equal to mass into acceleration, right? Centripetal force is mr omega square, means net force is mass into acceleration is what we are writing. This system you are given here is not a point object. It's an extended system. Can one of you tell me how to apply Newton's second law to an extended system? Or, okay,
Equal to M into acceleration of center of mass.
good, good, good. Okay. What I wanted to say is this is a rotating system. Fine. In rotating systems, different points will have different accelerations. Then how to apply Newton's second law to such a system? You write F net is mass into acceleration of center of mass of the system. Okay. Now this is a cylinder filled with liquid and we are assuming ideal liquids. Ideal liquids are incompressible, means the density will be same everywhere. Okay. If the density is same everywhere, it means it's a uniformly distributed mass. For a uniformly distributed mass, the center of mass will be the midpoint itself, the point of symmetry. Okay. So this is the center of mass. And you can visualize it going around. Center of mass is going around L by 2. So in place of R, you are supposed to take L by 2 because you are writing acceleration of center of mass. That's all. That will give you the answer now. So P2 minus P1 multiplied with S is equal to what? How much is the mass of the liquid inside this cylinder? Density into volume. How do you write volume? Area of cross section multiplied with the total length. So that's the mass multiplied with The radius in which the center of mass revolves is L by 2 multiplied with omega square. That's all. S gets cancelled. The area of cross section at A is rho L square omega square by 2. Okay. And not just A and B, you can take A and any other random point also. Okay. Between A and B, the distance was L. So we got this answer. But suppose you want pressure at some other point minus pressure at A, then the answer will be rho omega square. Instead of L square, you'll have x square, where x is the distance from A to that point divided by 2. And this is an interesting result. Why is this interesting? When a liquid is rotated, the pressure varies quadratically with the distance. X square, proportional to x square. Okay, this is not a linear variation. So in this case, the horizontal pressure variation is not linear. Now, you all might have observed something like this. When you try to stir water in a glass, okay, water, milk, or any liquid, when you stir it in a glass, you see something like this happening. When you stir a liquid, effectively you are rotating the liquid. Okay. You can see both cases, non-rotated liquid and a rotated liquid. When a liquid is rotated, you observe the free surface, how it looks. It's somewhat like this. It is not linear, but see, this is a real situation, right? Real water. Real water is not ideal. Okay, so viscosity will be playing a role here, due to which you get the shape like this. Okay, but ideally, if you consider a container and rotate a liquid with constant angular velocity, in real life, maintaining constant angular velocity with free hand is very difficult. Okay, so you won't get the perfect shape in real life. But if you imagine a situation like that, where the liquid in a container is rotated with constant angular velocity about an axis passing through the center, you will see that the liquid settles. Okay, as I said, this is an ideal case. We are ignoring the effects of viscosity and all. You'll see it settle like this. Why won't it be straight? Okay, why can't it just be like a cone? Like when you see from the side, why can't the boundary be? Why should it be shaped like a bowl? Let us discuss. We just saw that when a liquid is rotated, horizontal pressure variation varies based on x square. But vertical pressure variation, vertically, the pressure varies due to gravity only. And pressure variation due to gravity is P naught plus rho gy. So vertical pressure variation is linear, horizontal pressure variation is quadratic. Okay. Now, let's try to derive an expression for this surface. We actually want to derive the shape of this surface. So what shall we do? We'll take one point here, call it as B. Take one point here, call it as A. Okay. And take another point below A, which is at the same depth as B. Let's call it C. Now between B and C, distance as Y. Okay. Now A and B are both exposed to atmosphere. So pressure at A is same as pressure at B, which is atmospheric pressure. Whereas pressure at C, you have two ways of expressing it. You can express it in terms of the depth Y. You can express it in terms of the distance X also. Okay. In terms of depth Y, if you see, it will be P naught plus rho G Y. In terms of horizontal distance, if you see, it will be pressure at B, which is P naught plus rho omega square x square by 2. We had just derived this. Okay. How do you do that? You can imagine a cylinder rotating like this. This distance is x. So pressure variation becomes rho x square omega square by 2. Now these two are equal. Both ways we wrote the pressure at point C itself. So equate them. When you equate them, you get rho gy is equal to rho omega square x square by 2. Rho gets cancelled. That's all. So you get y is equal to omega square by 2g, which is constant, multiplied with x square. And whenever you have something like y is equal to some constant into x square, the graph is a parabola. Quadratic equation, you know the graph will be a parabola. Okay, so if a liquid is rotated with constant angular velocity omega, the free surface of the liquid, its cross section will look like a parabola. But see, you know, it's a three-dimensional surface. It's like a bowl, right? You call that kind of a bowl as a paraboloid. Right? That is the shape that you get. But this is for an ideal liquid. A real liquid will not form this kind of a shape because in a real liquid, viscosity effects will be there. It's very hard to rotate the entire liquid with a constant angular velocity omega. If you do it, somehow manage to do it, you will get a paraboloid shape like this. Okay. So from the side, if you see, the boundary looks like a parabola. It won't look like a cone. It's not linear. This is not the shape that you see. Right. So let's quickly go through what all we discussed in today's class. First, we talked in depth about what happens when a container is accelerated downward with an acceleration equal to g or more than g, how the pressure varies. So if acceleration of container is equal to g in the downward direction, pressure in the liquid will be uniform. Upper surface will be at atmospheric pressure P naught. Lower surface will also be at P naught. If the container goes down with an acceleration more than g, then pressure will decrease as you go down. Instead of increasing, it will decrease. Okay, we discussed the functioning of a suction holder. And if the container goes down with an acceleration equal to g plus P naught by rho h, which is the maximum acceleration the liquid can manage, then the pressure at the bottom will become zero. If container accelerates any faster than that, liquid cannot keep up with it. You will see a vacuum. I mean, you will see an empty space forming there. Okay. And we solved one problem. And then we discussed, after that, the discussion was about the free surface of a liquid. Remember, the free surface of a liquid always settles perpendicular to the direction of pressure gradient, maximum pressure gradient. Okay. So when a liquid is simply placed in a container which is in equilibrium, pressure gradient is in the downward direction, vertical direction. So liquid surface settles horizontally. We explained why that happens. If you accelerate the liquid horizontally, then horizontally also you'll be creating a pressure variation. Vertically, due to gravity, it is there. Horizontally also you are creating. So the effective pressure gradient will be at an angle, and the liquid surface also settles at an angle perpendicular to the effective pressure gradient. We derive that angle in two different ways. Okay, easy to remember, tan inverse A by G with the horizontal. Then we talked about pressure variation in a rotated liquid. Okay, and using that we derived the equation for the free surface of a liquid rotated with constant angular velocity. We proved that it's a parabola. How did we prove this? Remember the idea also. We take 2 points on the surface first, which are obviously at the same pressure. Then we take some point inside. Then the pressure at the point inside will be written in terms of height and also in terms of this horizontal distance. Equate them, you'll get a relation between height and the horizontal distance. In this case, the relation is y is omega square by 2g into x square, which represents a parabolic variation. Okay. So the shape is a parabola. In 3D, you call it a paraboloid. Okay, so we have discussed thoroughly about how pressure varies in a liquid. Then next class, we'll talk about Pascal's law, hydraulic press, barometer, manometer, how atmospheric pressure is measured. Okay, what happens if you put that instrument in an elevator? Those cases we'll discuss. After that, we'll be able to talk about buoyant force, Archimedes principle and all. Okay, next class will be on Saturday. Tomorrow I won't be able to take the class.